Alright, so we're still inside this one quantitative variable part 2 notes, and in class last time we looked at doing a hypothesis test for a quantitative variable. Now the reason I chose to do the hypothesis test in class is because generally, again, we're still struggling a little bit with hypothesis testing. Comparables are generally a little bit easier, so that makes for a little bit easier of a video since you can't ask me as many questions when we're doing a video instead. So if you remember, there are 4 steps for doing a confidence interval. The second and third one are actually here for us, so let's make sure we also talk about what the first step is. So remember, the first step before was we listed out what P represented in words. And the reason why we talked about P was our population proportion. Proportions were for categorical variables. So we're working with quantitative variables now, so we're no longer talking about proportions, we're talking about means. So now instead of knowing what the population proportion is, I want to know what the population mean is in words. So that's going to be our first step that we're doing. Our second step for a confidence interval is our conditions, which are listed here for us. Now the first 2 conditions are exactly what we've already been seeing, right? We still have this relatively random and unbiased sample. We still either need to know it's normal or have a graph to look at to see if it looks symmetric and unimodal, or we need to sample at least 30. And again, just like with the hypothesis test, there's this third condition that I added that's because sigma, or the population standard deviation, is unknown. And the main reason why that is there is it's sort of a reminder of why that t distribution keeps showing up instead of the z distribution that we were used to. So that's again the kind of that reminder of why that third condition is there. But also what I want to remind you is the population standard deviation will be unknown, but S, the sample standard deviation, actually will be known. So I will still have a standard deviation, it's just now for the sample instead of for the population. Our third step is to actually do our calculation. This is what our formula is going to look like. Now remember, once I have my data set, I'm going to actually have most of these numbers, because y bar is our sample mean, S is our sample standard deviation, and n is our sample size. So those are all things that we're going to get once we have our sample. The only thing new here we have is this t. And so t is going to have to come from somewhere. Now, so kind of let's think back to when we did a confidence interval for one categorical variable. When I wanted to look at that, so I'm actually pull up that formula here real quick. So this was our confidence interval formula for a categorical variable. And so we had this z that showed up. Now how we found z was strictly based upon the confidence level. So if I was 95% confident, I used a z of 1.96. Versus if I was 99% confident, I used a z of 2.58. And when we did this, I'm trying to remember what that looked like, right? I would draw my picture, right? I would put my certain level of confidence in the middle, and then I would kind of work backwards in my table to find my number at the bottom. So the thing that I want to remember right now about my t, the t is going to come from a table. So it's not a calculation. And the biggest thing I need to know to find it first, which should make sense, is my confidence. So depending on how confident I want to be, that's going to affect my t. There's actually another thing that I have to note since I'm talking about a t that I didn't have to worry about for a z. What I also have to worry about for a t that we discussed in the video last time was the idea of this degrees of freedom that a t has, which we mentioned was based upon your sample size. So depending upon how big our sample was, we could put more or less trust in our numbers that we had. The degrees of freedom here for this is just our sample size minus 1. And so what we're going to look at, this is probably the easiest table that we use, is our t-table for intervals. This is also out on Blackboard for you. So course documents, tables, and formula sheet. That last document is the t confidence interval table that I just pulled up here. So there's the 2 different things that we have to know. We're going to have to know how confident we're going to be. So I'm going to have to give you a number that's on this table. I can't give you like 93% that's not on here. I have to give you something that's on the table. So we're going to have whatever level of confidence we are, that's going to tell us which column to go to. And then for our degrees of freedom, that's just going to tell us which row to go to. So confidence is my column that I go to. Degrees of freedom is going to be the row that I go to. Just for example, if I want to be 95% confident and I have 10 degrees of freedom, I'm going to go to the 95% column, the 10% row, and that's going to be my T. Generally makes a little bit more sense after we do our first example. So, let's look at our first example. So a company is interested in estimating the annual mean out-of-pocket employee health expenses of their employees. So take a random sample of 66 employees and found the mean out-of-pocket employee expense for the year was $1,752 with a standard deviation of $1,186. Now, so the thing to notice here, so this 1,186 is coming from just those 66 employees. So it's coming from just the sample, so that's why that's a sample standard deviation. We're going to do a 95% confidence interval for our parameter of interest. Alright, so our first step, now that we're working with a quantitative variable, is to define what mu is in words. So this is going to be our population, annual mean, out-of-pocket expenses, for employees, for this company. So I'm looking at the annual mean out-of-pocket expenses for employees for this company. So that's what I want to know. Our second step is our conditions. Let's see, it says that we take a random sample of 66 employees. Not much given to us there. So we're good. Our second condition is we either need to know that it's normal or have a graph to look at to assess it, or have a sample of at least 30. I wasn't given a graph to look at. It doesn't say it's normal in the problem. So here my 66 is at least 30. So we're good there. And then finally, the population standard deviation is going to be unknown, which is true. But again, remember, we actually do have a standard deviation. It's just the sample one here instead. Right, for our third step, we're just doing the formula. So if I go back and look at my formula here, I know Y bar, I know S, I know N. I just need to find T before I can actually continue on. So let's find T. So what I need to know is how confident do I want to be? Well, it tells me in the problem that we want to be 95% confident. And then I need to know my degrees of freedom, which is my sample size minus 1. My degrees of freedom is going to be 65. So we're going to pull up our table, 95% column, and then we're trying to find the 65 row. And I did this intentionally. If you'll notice, there actually is not a 65 row. It goes from 60 to 70, and you do get a slightly different number depending upon which way you go. Now, first of all, when it comes to any homework assignments, quizzes, an exam, if you use the 60 or the 70, I'm not going to be upset either way. So if you use this 2.000 or the 1.994, I am perfectly happy with that. I'm going to tell you what I do and kind of explain why. So when it comes to degrees of freedom, I always round down. So even if it was 69, I would actually round it down to 60. And my quick explanation as to why is degrees of freedom is based upon sample size. And so I would rather underestimate my sample size or pretend I have less data than to pretend I have more data. So I will have a tendency to round down, and so I will use the 60 for that reason. So my T is going to be 2.00. And then at that point, we have all of the numbers to plug in. So again, formula just here on the previous page, probably on your same page that you're looking at right now. So we're going to take our sample mean, which was 1,752, minus our T times our S over the square root of N. Then the same thing on the other side, except there's that plus sign between them. And again, just as before when we did a confidence interval, you don't have to show me that in-between work. I recommend doing it here because we're going to talk about a couple of those terms that we've seen before. But in a general standpoint, you show me what you plug in and the final numbers, and that's perfectly fine. But again, it's making sure we do our order of operations correctly. I'm going to first find what's in my parentheses here. Then we're going to do our multiplication. And then finally our subtraction and our addition. Here I rounded things to 2 decimals since we're talking about money. There's the math done for us. That is kind of a quick reminder of some terms that we've talked about. So this 145 number, that's our standard error. And this 291 number is our margin of error that we have. From that margin of error is what we add and subtract from either side. Standard error is like our estimated standard deviation. So notice how those terms relate to our quantitative variable. And our last step, of course, when we've done pretty much everything we've been doing, is to interpret it. And our interpretation here is going to look a lot like what we did before. So I'm always going to start with how confident I am. And then here we're actually going to kind of go back to step 1. So we're going to be 95% confident that the population annual mean out of pocket employee health expenses for this company lies between $1,460.03 and our $2,043.97. And that's what our steps look like. Now, a couple of notes about this. So our first note that's important. This is not telling us about individuals. But I want to figure out how much an individual employee spends on out-of-pocket expenses. This is not what I look at. Chebyshev's rule does this. Alright, that's looking at an individual. This is on the mean. So out of all the words people think I'm picky about here, the word mean here is actually very important. A great way to think about that is if you think about looking ahead to the exam 3, and suppose you want to know how do students do on average. And if I say, well, I'm pretty confident, 95% confident, that the mean exam 3 score is going to be between a 70 and an 80. That does not mean that 95% of my students are scoring between a 70 and an 80. That's where I expect the mean to be, right? So knowing about where the mean falls is very different than how do individuals fall. That's what Chebyshev's rule tells us about. So be very careful. This word mean here is important. This is where I believe the mean is, not where individuals are. My other thing I want to talk about here is actually more of a question of sort of relating things back. So one thing that we talked about before is that we like narrower intervals. So how could we narrow this interval? If you look at this interval, it's pretty wide. I mean, it's almost $600 wide. So there are two different ways that we could narrow an interval. The first way that we talked about was by decreasing our confidence level. But of course, we talked about the downfall of that is you're less confident. The other way that we could narrow our interval was to increase our sample size. So now that you've seen an example of a confidence interval in class together, next time we'll do another hypothesis test and a confidence interval example together.